Okay, um, so continuing to go through our table of famous discrete random variables, I want to talk about two other random variables that, like the binomial, are based on Bernoulli trials. Okay, the geometric and the negative binomial, and they kind of, in my mind, go together with the binomial and kind of a group. As the questions that they answer are related. Okay, so let's kind of zoom in on those three. And we talked about the binomial in the last lesson. The geometric random variable is, in one sense, the simplest one. Like the binomial, we're talking about some number of independent Bernoulli trials, independent coin flips, independent trials that can be a success with probability P or a failure with probability 1 minus P. That's the only outcomes they can have. And the geometric random variable tells us the number of trials until the first success. So what's the probability that you get success on the first trial? That's pretty easy, that's P. What about the probability that it takes 2 trials, that it takes 3, that it takes 4, etc. Okay, so the PMF for that, the probability that the first success comes in the ith trial is 1 minus p to the I minus 1 power times p. So I'm just going to copy that down below here. The geometric. And really, this is a pretty simple PMF to understand, because the event that the geometric random variable talks about has only a single outcome in it. Okay, we're asking what's the probability that the first success comes in the ith trial. Okay, so there's only one outcome associated with that, and it is I minus 1 failures, okay, followed by 1 success. Okay, so if we're looking for the probability that the first success comes in the fourth trial, what we're saying is that is the probability of fail, 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 success. And what is the probability of that outcome? It is each of these fails happens with probability 1 minus p, and that success happens with probability p. Okay, so it's each of these fails happens with probability 1 minus p, and there's 3 of them, so that's 1 minus p to the third power times the probability of p. Okay, so really not much more to say about that. The negative binomial is a little more complicated. It's kind of generalizing the geometric random variable. So the negative binomial asks, how many trials do you need to get R successes? And I think the idea behind using the letter R is it's a required number of successes. And that probability is a little bit hairier. Let's take a look at it. Binomial, PMF, what am I doing here? Probability that it takes I trials to get R successes is I minus 1 choose R minus 1 times P to the R times 1 minus P to the I minus R. Okay, that is a pretty weird looking PMF. But again, let's just kind of think about what's going on here. This is the probability of R successes followed by I minus R fails. And that is indeed what we need to have, although we need to have it in the opposite order, for the negative binomial, we need to have the success come at the end. But that's okay. This probability is the probability of any combination of R successes and I minus R fails, right? So going on here, R successes, I minus R fails. So the required number of successes and the rest of them, the rest of the I trials being fails. So that kind of looks like the binomial there. And it is a lot like the binomial, except that this is different. Instead of I and R here, we've got I minus 1 choose R minus 1. And that's because your last success has to be at the end. The first R minus 1 successes, they can be anywhere. Okay, they can be anywhere in the I minus 1 first trials, but the position of that last success is pinned down by the question being asked. Okay. All right. One thing I should say about the negative binomial random variable is this basic idea can get talked about different ways. So this is the way I'm doing it is one way that you'll see the number of trials until the Rth success. Sometimes people will talk about it as the number of failures that you need to get a single success, and it is exactly the same idea, but the PMF looks different and the parameters look a little bit different there. So if you're reconciling what we've got in our table with what you see in a book or something like that, it might be the same definition of the parameters, or it might be slightly different. They are capturing the identical ideas. Yeah. That's more in the weeds than we need to go here. We could go through a little more analysis to derive the formulas for the expected values and the variances here. We're not. We're just going to accept them as being correct. And what I want to do in the rest of this lesson is apply these random variables to some more specific questions. Okay, so what I have in mind for kind of the more specific questions, I'm thinking of a scenario where you're what are we doing in this scenario? Asking friends to help you with something, help you move. We are assuming that each friend says yes with probability 0.6, okay? And that the friends' answers are independent. That wouldn't be true for my friends, but it's an example of those kind of independence assumptions that we make because it seems acceptable. Okay, so answers are independent. And back on the independence thing, it's a kind of assumption that we make because it makes our lives easier, it makes our models simpler, and it's sometimes a reasonable simplification. So in this problem, we're going to assume that the friends are all from different social circles, and whether one says yes doesn't depend on, isn't affected by whether another one does. And what I've got here are like examples of questions we could ask there. What's the probability that you need to ask 5 people in order to get 3 helpers? If you ask 6 people, how many do you expect to say yes? If you are looking, what's the variance of the number of people you have to ask until 1 says yes? So what I want to do quickly is map each of these questions into answers that are lurking in our lovely table here, okay? So for the first one, the probability that you need to ask 5 friends in order to get 3 helpers. So this is a number of trials to get a required number of successes, okay? This is a negative binomial with R equals 3. Okay. So one thing we're trying to decode in these questions is which of the related random variables is the question asking about. And the other thing that we need to decode is like, what is the question asking for? Which column are we in? Okay. That seems sort of obvious, but it's an easy thing to forget. So what we're looking for here is the probability. Okay, so this is a question about the PMF. So what we want here is the probability for negative binomial that we need to ask 5 friends in order to get 3 helpers. Okay. So we've got r equals 3. We don't have n equals anything because it's a negative binomial. We've got I equals 5. I'm having trouble writing today. Okay. The number that we're interested in is 5. And the other thing we need to is p. Okay, and so p is that 0.06 that I'd assumed before. Now we can just map things into the negative binomial PMF, and let's remind ourselves what that is on just in abstract. Okay, it's I minus 1, choose r minus 1, p to the r, 1 minus p to the I minus r. Okay, and so that probability is 5 minus 1, choose 3 minus 1. Okay, I minus 1 is 5 minus 1, r minus 1, 3 minus 1, times my p is 0.6 here, 0.6 to the power 3, and 1 minus p, 0.4 to the I minus r power, the second power. Okay. So 4 choose 2, that's what this is, 4 choose 2 times 0.6 cubed times 0.4 squared. That gives you a number, and that number is, can I punch it out? 0.2074. Okay. With all of these probabilities that are based on Bernoulli trials, somewhere in the probability lurking is going to be the probability of a specific outcome that is going to have in the exponents the total number of trials. Okay, so that's always going to be there, and it's because we're building up this probability from the probability of however many trials we have being multiplied, and we can multiply them because they're independent. Okay, so the number of trials for the negative binomial here is our I. That's the question we're asking. How many trials to satisfy the R criterion? So our I here, we should see the exponents adding up to that. And indeed, we see it in the formula here. R plus I minus R is I. All right, that was maybe more of an elaboration than I needed. Kind of the main point here is figuring out what we're being asked about. Is it a probability? Is it an expected value? Is it a variance? And what kind of random variable are we talking about here? Okay, so what kind of question is being asked? It's a negative binomial type question here. Another question that we might have here, if you ask 6 friends, how many do you expect to show up? How many do you expect to say yes? Okay, so here we're being told a number of trials, and the thing we're wondering about is how many successes are we going to have? We're asking 6. How many will say yes? So that when the number of trials is given as a parameter, that's letting us know that we have a binomial. Okay, and binomial with n equals 6 and p, as it was before, is 0.6, and we want the expected number who will say yes. Well, here we're just being asked for the expected value of a binomial random variable. Read it right off the table. It's n times p. It's 6 times 0.06 equals 3.6. Nice and simple, right? That's all there is to it. Um, very last one. The variance of the number of people we need to ask until one says yes here. So apply that same principle here. First, let's think about which random variable this question applies to. Well, we're looking for the number of people to the first success. So this looks like a geometric random variable. Number of trials till first success. And what we're being asked about here is the variance. And again, we can just read it right off the table, okay? So the variance of a geometric random variable, that is 1 minus p over p squared. You're right, we didn't derive it. You can look up the derivation if you want to, but for the purposes of 200A, that's kind of more into the details than we need to go. For our purposes, we can just use the formula, plugging in our numbers. Remember, we have P, probability of success in each trial, being 0.06. So the variance formula is 0.4 divided by 0.6 squared. And for that, I get 1.11. Okay. So there's tons and tons of little like practical questions you can answer using these random variables based on Bernoulli trials.